You don't, what, you don't think it should be?
I don't know how to spell Tennessee, but I can tell you what it is.
Don't take it out on me.
Embarrassing.
It's always a hard thing, like there are things I don't even take things out on. But school policy, I have to take it out on everybody.
I kind of like it. It kind of like apple.
Oh, my hand.
And I'm glad you got the sugar-free one.
They're good.
I love it.
I like Brandon. The new Red Bull tastes like the. Oh my goodness, you're the best. Where's apple lollipop?
Did you cut them up?
I want to try
the
pomegranate one, but you have to get the advent calendar to try the
$2 advent calendar.
I love you. Bye.
Okay, so you remember how
I'm
we
considering it
found,
just to try the pomegranate. I'm considering.
we found this new formation, second line.
I agree with that. You know, we have the frozen
Seeds on
three?
it.
They're coming with the Frozen 3s.
Yes,
Are you serious?
yes, and a Toy Story 5. What is?
Toy Story. Why are they gonna continue about Toy Story?
Zootopia 2 looks good.
Yeah, it
I
does.
wanna watch that one.
I like the first one.
Which one?
I've never seen the second one.
The only Frozen I knew about was the Frozen 4.
I say this shit out.
Frozen
Do you have any idea who the Frozen 4 is? College ice hockey, it's the same thing as the Final Four, but it's the Frozen.
Okay.
I don't watch hockey. We're from Nebraska.
No.
We don't know what hockey is.
No, there's one in Kearney, Tri-City Storm, guys.
Again, I don't know. What.
So we have the formulation of Newton's second law in terms of torque.
Look further.
I don't even know what to do with this.
We have medical school.
Maybe I'll make the final easier if you can tell me who the wizard is that summons the Great Begawa.
That sounds like a great one.
Great Begawa.
That's all you're saying.
Shush. You've already told, so shush.
All I got is Harry Potter. That's as
Nope.
close as I get to. Well, I know it's not Harry Potter, but that's as close as I get to down.
There is a wizard who will summon the Great Begawa.
Maddie, I miss you.
Some other crap sin.
He's like, dude.
My bed last night.
I was asleep.
I just heard he said make the final easier.
Here.
I'm just like,
You're jumping on it.
I'm good, yeah.
Okay. Speaking of which, as I'm working on this pre-engineering thing, my Dr. Soto had like idea things, something I've never seen before.
But I was like, oh, that.
Production and a number of different things. Did you know that there are?
She find out right afterward.
It's a biological house that can be put inside of this.
I hope she gets it.
Electrodes and different stuff in it. Yeah, it's a bioreactor.
I've heard that.
She said if you.
Would you have ever had
I had no idea that
I
bioreactor.
wish we had more bananas, so I. Banana bread.
Good.
Don't worry. I need six. It was too low.
Okay,
Yeah,
so
true.
YouTube,
Yeah. Ever. I know where it is.
we're gonna move on to this.
Oh.
Okay, so we have a solid grinding wheel, it's uniform disc of 2.5 kilograms, radius 9, so you can read, I think you can read. I did have one of you in this class tell me you don't know how to use a textbook, so I do worry.
Don't know how to use a textbook?
Yeah, don't know how to use a textbook.
Who said that?
It's textbook case.
Find the angular displacement of the wheel using equations for constant alpha.
Just use yours. But it don't make sense. You ever watched that movie?
What is
I
alpha?
watched that movie. That was the best movie.
I've watched it so long.
Maybe
Alpha and Omega.
It's not a Christian movie. You may think.
I watched Big Hero 6.
That's a heartbreaking movie.
I'm working.
You think that's traumatic? You need.
Right, we're just drama dumping over here.
Color.
No.
It's
You just watch Bridge to Terabithia. To yourself. I don't know. It wasn't my choice. It was someone else's.
Don't ever watch an M. Night Shyamalan movie, because what was that? Shape of Water?
Liam said we
Where
do.
the lady in the movie just had an infatuation with the fish person?
What?
Oh,
No, it's-
okay.
That's not what they're all like.
I thought you were talking about the Avatar movie that came out.
Which I don't like that they called that franchise Avatar. Now we can't do any movies with the last Airbender and call it Avatar. That's.
And the new Avatar comes out in December.
True.
The new Stranger Things series comes out.
What?
It's soon.
Anything?
GTA 6 is coming out next year.
No, Stranger Things.
Yeah.
Season 5.
Next year.
Yeah, but apparently
Yeah,
now that
so
Disney
Jake
owns the
was
Predator
May,
franchise.
in November,
now
so
it-
I'm gonna like struggle.
So Disney ruins another franchise.
In all honesty, it's gonna get pushed back.
Yeah, it would be.
Wait, so,
This is what I'm saying, like-
no one answered my question. What is alpha?
26, straight.
And you,
What's that? We actually have a book.
It's a Greek letter.
angular acceleration. When I say equations based off constant angular acceleration, what equations are those?
I know.
A wolf.
I'm not.
The momentum or the inertia.
Nope, we did it a couple chapters ago. What equations would you use to solve a system in motion with constant acceleration?
Can I draw the meth molecule on her ornament?
It's so not.
Equations that solve a system in motion with constant acceleration.
Driving off. Yeah, I said that really loud.
If I have to go make a stupid ornament, I'm gonna make it that.
So much fun.
I'm gonna draw a meth molecule.
This is close to gluing a hook to your head and hanging from the ceiling.
Bro.
What if I ornament I buy?
Oh, yeah.
The all. So nice, Eva.
Constant acceleration, list of
See the
equations,
potential.
constant acceleration.
What else? The-
You just mean like the sum of the acceleration.
Did you? You have to talk louder than the person next to you for me to hear it.
Oh, that's really hard. Really hard.
Okay, so find the angular displacement. The angular displacement will be what? So how do we represent that? So what, your displacement in, say, the x direction is delta x. What is it in angular motion? Delta theta. So we can say theta.
We put it together.
One of these is zero. Which one? Can you see why the problem?
I don't. Starting from rest.
Yep, starting from rest.
Yeah, I might just be like. Yeah, exactly.
Now, how do we find that final angular speed?
Yeah, I know that.
Not given.
Well, kind of.
So it's not like for sure. Science.
Kind of is. What units does angular speed have to be in?
Oh, you want it to be in radian?
Yeah, radians per second.
Just come over to our house.
So what we have,
So
Oh, no, a giant whiteboard.
Yeah, I guess.
126 revolutions per second. How many revolutions,
Did you see
radians per revolution?
Karaoke.
2 pi.
$20. Don't buy it.
Oh.
So now we have our final angular velocity or speed. Plug this in.
It's only $20. It's like a portable one. I put in $160, I guess. As a joke, I did, because the limit's like $20.
So you're gonna get about 2375 radians as your delta theta.
That's the Lego set I put on my shoes. I mean, I support for my friend. They just don't want me. That's what it is, if they don't get me.
Okay, part B. I think it should say, find the change in rotational kinetic energy of.
Secret Santa. I also put 308 on there.
What towels?
I saw that.
And a charger for it. No.
What do you need that charger for? You don't have an iPad.
Now, what does this look like? So this is back to what you were talking about. Yeah, the inertia. So what is kinetic energy for rotation?
I alpha.
Close, it's 1/2 I. Not alpha.
Oh my god.
Yeah, so always compare it to linear kinetic energy. MV squared, but instead of M, you put in inertia, and then V, you put in omega.
I see.
Force starts from rest, so that one goes to 0. Now, this is a solid disk. Do we remember what the inertia for a solid disk is?
No.
You can either derive it like we did in class, or you can just look it up off the list.
Let's look it up off squares.
What?
MR squared.
Close.
Which one uses this?
So think of it as a solid cylinder.
Okay, 1/2 M times A squared plus B squared.
Nope, that's a hollow cylinder, solid cylinder.
Oh my gosh. Today, answer my
There you
first
go.
question. History of our own. I'm speaking my class.
So we look up the inertia for a solid disk, which is a very short solid cylinder. Yeah, and keep in mind your cylinders, you had 3 of them. You had a solid cylinder, a hollow cylinder, which is your A squared minus B squared, and then you had a very thin hollow cylinder or cylindrical shell.
Nobody else sees her. She's dead. No.
So we can put that in there. And we're gonna end up with 1/4 MR squared. Make a final squared, and then we can plug in numbers. Oh, let's see, M is 2.50 kilograms. Put in the omega, well, the omega we found in part 1. And the change in kinetic energy is going to be 3173 joules. Because this leads us to part C.
We're going way too.
Yeah, he's well.
There's 2 possibilities. I could be going too fast, or there could be 2. Crap, I didn't write that down. That could also be part of what's going on.
On the last part, you went too fast.
I knew I was not gonna actually win that argument, but I figured I'd throw the suggestion out there.
8.
So parts A and B, if you notice, were designed to lead up to part C. Find the torque on the system given that the work done on the rotation. Torque times delta theta. And of course, we found delta theta. We need to figure out what the work is. What is the work gonna equal? It could be, yes. There we go. So the torque is then going to be 3173 joules over 2375 radians. 1.34 joules of torque energy. Remember to bring back your work energy theorem. Okay. The motion of rolling objects. You will see that the rotational kinetic energy is going to be proportional to the translational kinetic energy by 1 plus some number beta. Okay, so let's think about a rolling object. The radius, center of mass. You have the translational motion, the translational velocity as tangent to the curve of the rolling object at each individual point. You also have the overall velocity of the center of mass. And of course, we remember translational velocity is r omega. And then we also remember that the velocity the center of mass no, not R. There we go. But we only have one mass that we're looking at here. It's going to be rotational velocity over m, which means so you see that your translational velocity and the velocity of your center of mass are going to be identical.
Per head.
So we just got cameras at our house, Dr. Everard, and there's like a mama raccoon with all her baby raccoons.
Oh,
Yeah, she's fat too. She eats all of our cat food.
the panda family.
Yeah.
Okay, now let's start thinking about where this beta comes from. You're going to think of this in terms of, let's just say a wheel rolling down a hill, okay? Now we've seen repeatedly that the moment of inertia is going to be some pure number beta multiplied by mr squared. So for example, solid cylinder is what? 1/2 r squared. Beta equals 1/2. So again, you've seen this repeatedly, even with that hollow cylinder where you have a squared minus b squared, that's still that a squared minus b squared is the difference in radii. So what beta is going to be a measure of is the distance of, so how far from the axis of mass is going to be distributed. So your axis of rotation, of course, would be at that center of mass. So then we say, how does beta work into this system? So we can start here. And of course, from up above, we get that your omega is going to be velocity of your center of mass over r squared. I'm trying to get my writing better, but I didn't eat anything today and I've drank a lot of coffee, so I'm a little shaky. No. I even put some of the Death Wish coffee in my coffee pot this morning.
Not like a ton of caffeine.
So you can get it at Walmart. Death Wish coffee is twice the caffeine of regular coffee. I still think we should go to the chemistry stock closet, get the big jar of powdered caffeine, make up a solution, put it in an insulin pump, hook that thing up and just tap the button all day.
Okay. I need that honestly right now.
Okay, so
Caffeine.
okay, let's try to, okay, so
I didn't put propel on here.
I was going to. I didn't.
so when you end up solving this, you're gonna get beta 1/2.
You know anyone that gets me, make sure they get me for that.
Okay.
So 1/2, so okay, so now the beta times 1/2 mv squared. 1/2 mv squared is the kinetic energy of what? So, yeah, so translational kinetic energy.
That you found the package that with the neurons. And the other propel package.
I do have a little bit of email.
So kinetic energy translational.
Yeah, it's like.
Linear motion.
It's just.
Yeah,
So it's like the tangential.
yeah. You can also really bring it back to molecular motion. The translational energy levels are molecules moving like this. They're just translating from one spot to another.
Oh.
Okay, so if we do total kinetic energy. K rotational plus K translational.
Show the picture.
So I'm right there.
It's so funny. I can show you the picture after. All he sent us was that picture. This is, how do you get rotated like that?
Oh, yeah.
Now, you notice if we factor,
I was
factor,
dying for a good like 10 minutes.
factor out the beta or factor out the 1/2 mv squared. And because beta plus 1 equals 1 plus beta, you can now say that the total kinetic energy and so there you go. So your total kinetic energy is going to be this 1 plus beta factor of your translational kinetic energy. This is probably the most abstract part of the chapter, so do the best you can to follow it. Go back to the chapter and check through it. So then we can use this. What fraction of a rolling ball's kinetic energy is rotational kinetic energy? Going to have translational, it's going to have rotational. What fraction of it is rotational? So first off, we have to ask ourselves how to set up that fraction. Well, the fraction would be rotational over total. That's what we're trying for. So we can say rotational kinetic energy inertia around the center of mass, omega squared over beta we can start there. Now we look up, we look up a solid sphere, and we see that I so what's beta equal? 2/5. We'll use that in a little. We'll use that in a second. Okay, so okay, so you notice that the 1/2 and the 1/2 can cancel out. Your moment of inertia, beta mr squared, your omega, v squared over r squared. Plus beta. V squared. So now take a look here. R squared, M, V, V. So your fraction ends up being beta over 1 plus beta. So then you put in 2/5 over 1 plus 2/5. Who can solve that?
One,
2/5.
don't they cross out?
So it's 2/5 over 7/5.
Yep, 2/5 over 7/5. Okay, which is going to lead to
Well, you have 2 or 5.
2 times 5 over 7 times 5. Yep. So the fraction of that rolling ball that is rotational energy is 2/7 of the kinetic energy.
Five sevenths.
You notice how we've conveniently ignored your favorite numbers.
Seven's there.
7's there.
See, we don't even have to say it.
Now we have one more version of Newton's second law. Angular momentum. Oddly, it sounds like another Harry Potter spell.
would be arresto momentum.
No, that's one of the Harry Potter spells. This sounds like one. The difference is that this one's real. Really?
Until I figure it out.
You can't discount Harry Potter.
I was gonna say, I thought you were telling me that angular momentum wasn't real, in which case I was gonna make you all do a project on electron angular momentum within a molecule that contributes to reactivity.
Saying Harry Potter might be real.
Well, we all know lightsabers are better, so it's okay.
Well, you never got your letter to Hogwarts, so,
Yeah, and I regret that every day.
okay. Okay, so Newton's second law is now going to be the sum of all your torques is going to be, essentially it's your delta L over delta T, so your rate of change of angular momentum. Okay. How do we get here? I put this meme on here because I figured that would be everyone's response.
Yep.
Now, see, you did it very like sarcastically. SpongeBob's happy when he's doing it.
Is that when they're showing bubbles?
I don't remember.
No, it's
Now, so first off, let's say, okay, so angular momentum. It's going to have units. Kilograms meter squared per second. So those are the units you'll be looking for. You also notice that your angular momentum is your moment of inertia times omega.
So this have kind of like a similar word. Or am I not?
What?
You know, I'm just gonna ignore
Okay.
it.
I'm like, I need to have a comparison. I need to know what it's similar to if I can say it before I can say yes or no.
What do you say this was, linear momentum?
Angular
Well,
momentum.
linear momentum, of course, is P, and that's, your momentum moving in a straight line. Your angular momentum is the momentum in a spinning motion.
Is that what L stands for?
Yes, L is your angular momentum. That is pretty much the universal symbol for angular momentum in textbooks. Depending on the textbook, if they use a lowercase or uppercase L, but still L is going to be your angular momentum. You're going to see a lot of that starting next year with quantum chemistry.
I'm so excited.
Aren't you our teacher for that?
Some confetti.
Huh?
No, sorry.
Who's gonna teach it?
I should be, so for that, I should be doing the lecture portion, and I think Keith is going to take the labs.
So that means more divided equation.
You'll learn a lot more than what
Well,
I
but
did.
in chemistry, it's different. It's like we're trying, like in chemistry, we're trying to actually find specific numbers for a chemical system.
Will there still be memes on the slides?
Oh, yeah.
Okay, good.
Now, a couple of things we want to start with.
Precise commission.
Thanks.
Oh boy, okay, so
We just went close enough.
angular momentum,
Went with it.
cross product number one, R across your translational, your linear momentum. So again, remember how we were relating translational or linear velocity to rotation? Now, this is going to be our relating of our translational momentum to angular momentum. So then also, remember that torques are R cross F. Okay, so we start by saying So of course, you remember your limit is defining the derivative of this situation. I also, well, I'll show you that in a minute once we get there. Okay, so now we're going to change this into torque. So R cross F is going to be R cross now we're going to use the rate derivative, R cross P. That is going to be the definition of the rate of change of our angular momentum. So we need to use the chain, so we're going to end up using the chain rule. You have a derivative of this, of one thing times another thing. So that is your derivative chain rule. Take the derivative of the first one multiplied by the second plus multiplied by the derivative of the second one, and you could do it so on and so forth down through third, fourth, fifth, and whatnot.
Today's hard rule.
Okay, so okay, so now we've applied the chain rule to the cross products because those are that is a multiplication. To remind ourselves that momentum is m times v. Guys, first off, the derivative dr dt, does anyone remember what that is? Think of it as delta r over delta t.
The position over time.
And that equals what? The rate of change of position is velocity.
Okay.
Okay. So let's just work with that V cross P for a second. Definition of momentum. So we can pull out that constant and we get V cross V. So here's a question. When you have a vector that crosses itself, what happens? What does that equal? Nope.
0. Those are the two numbers.
A vector that crosses itself goes to 0. We can prove that. This is the part where we're going to have some real fun. I like it. I really felt that mean. Okay, so V cross V. I don't remember what this is called. Matrix, but what operation are we doing to it? This is the matrix determinant. Okay, so this is going to become, so you have your I hat. You need to pull out your sub matrix. Where your sub matrix comes out of anything that's outside of the row and column that your I, J, and K are in. And now that we have two by two matrices, we cross multiply and subtract. And another room over there, so we'll do K hat.
Yeah, I got 90. That's awesome.
And when you look at these, so that means when a vector crosses itself, everything goes to zero. That was just the simple matrix determinant expression of a cross product. So we remember this, so our that V cross B ends up becoming zero. Oh, sorry, that's supposed to be a cross in there. So then we go back to the definition of our Newton's second law, where we had R cross F equals R cross dp dt. And so we notice that the left side is going to be our torque. And now we know that our right side ends up becoming the differential, temporal change, the rate of change of angular momentum. And so we can translate this back into the discrete form. So we end up back, so what we do is we see that our now new expression of Newton's second law is going to be your torque is going to be the rate of change of your angular momentum of your system. Now we also saw that your angular momentum is going to be I times omega. So we're going to start with the fact that momentum, mass times velocity, velocity, omega times R. So we're gonna put in. We're gonna put in linear momentum here, and we're going to substitute in our omega. And so when you have your sum of m times r, what is that? That's your inertia. So your angular momentum in this case has to be your inertia multiplied by your angular speed. So on Wednesday, we'll solve one more problem and then we'll be going into the chapter on fluids.
Like water.
Yes, like, water, oil.
Hey, Liam, you guys leave for
Thursday. We come in